was amazing meeting all these people from all these places who've been facing similar problems as me or as the company. And it's nice just talking to people in the hallways after the talk, during talks, between talks.
Ladies and gentlemen, 300 seconds, maximum concentration, let's go. Example 1. We just sum in an array, the simplest loop ever in existence. On the right is the assembly representation, this is the Godbolt link. And let's take a simplified model of our CPU. Let's say all the array is in L1 cache, and each load will take 4 cycles to compute. And then add and compare will also take 1 cycle, which is standard on most modern CPUs. And let's represent our instructions in a data flow graph. This is how CPU would issue them in the slot of 1 core. Basically, we will start with advancing the pointer and starting with the load. And then on the right side, on the slot tree, you can see all the actual summation for the main accumulator variable. They will start from cycle 4 because it will take 4 cycles to actually load that first num. So here, by this orange color, I selected all the instructions that depend on the pointer variable, and you see that all the instructions cycle 1 that I selected is orange are dependent on pointer. So they cannot be issued before this instruction has been completed. That's basically a data dependency. And then this is the secondary data dependency, because the sum equals plus num is dependent on num. And this is how it progresses over time. So in this case, loop has a throughput of 1 summation per cycle. It is defined by the latency of the pointer advance, because we can only advance by one per each cycle. It is not influenced by load latency. What I mean, if the load latency was like 24 cycles instead of 4 cycles, it will just delay when the first load finishes and the first summation is issued by 20 cycles, but it will not be 6 times bigger, which might be like the first intuitive guess. So actually, in this case, optimizing full load latency wouldn't make sense. So in this case, pointer advance actually constitutes what's called a primary dependency chain, and we have a data dependency of a pointer variable. And for primary chains, latency is paramount. So in this case, latency of pointer advance is 1 cycle, and that's why it defines the whole performance of the loop. And actual summation and load of num considers a secondary dependency chain. Now, let's take a look at this example number 2. So in this case, I just split the summation into 2 subsums to try to speed this up the loop. So this is the data flow graph. And in this case, we see we will have 2 sums per each cycle. So some even and some odd. So now we're able to advance the pointer by 2 each cycle. By 2, I mean like by 8 bytes because we have integers, just like 2 integers. And then we can issue 2 loads per cycle because we have 2 sums, num even and num odd. And since we can do 2 loads per cycles, we can do so because our CPU permits it. On most modern CPUs, we have 2 load ports. They can be utilized at the same cycle. So basically, for the secondary chain, which comprises of actually loading data from this pointer and summing to the accumulators num even and some odd, the throughput is what defining the performance. By throughput, I mean how many instructions per cycle can be issued in parallel. And in this case, it's 2 instructions because we are limited by the CPU that can issue max of 2 loads. So overall performance is still dictated by the pointer advance, which is the primary chain. But its performance is now 2 per cycle, so by 8 bytes per cycle. Since we can, on the secondary chain, we can issue 2 loads per cycle. So the conclusion of my talk, and if you skip the entire talk, what I want you to memorize is when you have a tight loop with a data dependency chain, you have to identify the primary and secondary chain. For the primary, you have to look at the latency of the instructions. Now for the secondary, you have to optimize for the throughput because they kind of work with each other and kind of depend on each other. And that was my talk. So I'm a co-founder of Functio AI. We build agents. We use language models to optimize performance. So if this is something that you deal with on a regular basis, performance optimizations, come talk to me. Also visit our website. We're launching a product soon. And come talk to me here. Email me. Thank you.